Okay, so the next concept that we are going to discuss is the stress and strain which is developed uh, in a ring having film, having a soap film, right? So this is one very important concept over here, and the idea is that if there is over here a film in this way, let us say, right, and let us say that the radius of this film is nothing but equal to some r value. It is the radius of the film or the radius of the ring, both are the same over here. And we observe that by selecting a very small element of this particular ring element, we can find out what is the forces which are acting over here. Inside there is film and outside there is nothing but air over here, and this film has two surfaces, and we are not going to ignore the other surface over here, right? So therefore over here let us consider that this is nothing but the small element, and this is the center over here, and in this way you have the material of the ring over here, maybe some metal over here, or it could even be some rubber band over here, doesn't matter really. And the idea is that there will be a force over here that will be acting in which direction we want to decide, right? So the film over here will be pulling this particular will be pulling the small elemental length over here in this direction, which is at 90 degrees over here, in this way over here, right? And therefore what would be the counteracting force to this one over here? Because of the pull that is going to be radially inwards over here because of the film, this particular ring element will undergo a compression. It won't be extended over here, it will be compressed. So if it is compressed over here, then we can say that the elements which are around it, they will be exerting a force in this particular direction over here. This will be a compressive stress that will act, similar to how a rod over here will be compressed on exerting this kind of a force over here. In the same way, if it is a bent rod in this way over here, then this will be the compressive force that will be acting over here, right, due to the other elements. So therefore we can state that the compressive tension force, let that be equal to some value, let's call that as a T for now. It's not the surface tension, it's just the compressive tension force, compressive force over here, not even tension. So therefore, and it will be tangential over here, right? It will be tangential. Then we can write over here that if we take this particular angle, the angle bisector of this arc, let's say that this angle is nothing but equal to d theta, this angle must also be equal to d theta, and this total angle over here is nothing but how much? This is your 90 degrees over here, which means that since this line over here and this line over here, they're nothing but parallel lines over here, parallel to this particular line, right? These three lines are parallel over here. Then we can state that this angle over here must also be equal to d theta. So therefore we observe that over here this is the radial line and this is the tangential line, which means that this angle must be equal to 90 degrees itself, right? So therefore we can write that if this is your 90 degrees, then this angle over here, it must be equal to 90 minus of theta itself, right? Now if this is equal to your 90 minus of theta, then the component of the force which would be balancing this particular force, which is pointing inwards, the force of surface tension, the component of this T is nothing but how much over here? If you just extend this particular line, we can say that this angle must also be 90 minus of theta. That means in this direction you would be having t cos of 90 minus of theta, I mean t sin theta. And therefore over here again we can write that similarly performing the splitting of this t is nothing but t cos of another 90 minus of theta itself. That means t sin theta, which means that you would be having over here in the outward direction 2 times of t multiplied by sine of theta. Here the theta is very very small angle. That theta that we have taken is nothing but d theta over here. Please make that change, d theta over here, as well as this one is not theta, it is d theta over here. This one over here is also your d theta over here, and therefore we get 2t sine of d theta itself. Now this must be equal to the force which is pointing in the inward direction, and that is nothing but the force of surface tension itself. So over here this is nothing but the element of length dl, and we can write over here that this force acting is nothing but F multiplied by totally is nothing but the force of surface tension is equal to sigma. If this is the amount of surface tension which is nothing but the force acting per unit length, we can write sigma multiplied by dl itself on the front side, and therefore on the back side also you will be having one more. So the total surface tension force on the front side of the film as well as on the back side of the film, that means over here as well as over here, if you sum that over here for this particular film, you would be getting this as 2 times of sigma multiplied by dl. Now that we have the dl over here, let's write this in terms of d theta, right? What is dl? R times of the total arc angle, which is r times of 2 times of d theta. That's it. This total force of surface tension balances the compressive force which is acting over here in the outward direction, which is 2t sine of d theta, this particular value over here, right. The total force of surface tension Ft, this force over here, this is only due to the one film. There is also one film which is at the other side. That's it. Just write 2t sine d theta is 2 sigma r2 d theta, cancelling the terms, taking small angles. We get this t value as equal to how much? D theta will disappear, 2 will disappear by 2 times of sigma r. So now that we have this particular value, right, and therefore now we can write that if this is the amount of compressive force, then we can go to the Young's modulus and say that the Young's modulus is nothing but stress divided by the strain. The stress is nothing but the amount of compressive force per unit area, or the restoring compressive force per unit area is also the capital T that we have found out, divided by the area of cross section, divided by the strain over here is nothing but, let's call that delta L divided by L itself. Therefore we can write the strain amount, which is delta L by L, is T by A multiplied by Young's modulus, which means that it is 2 sigma R divided by A into Y itself, right? In some of these sources you will find that it is not taken as 2 sigma, it is taken as only sigma. So what they have done there is only selected only the force of surface tension due to only one film. They have not selected both the films, right, the front as well as on the back side, right? So therefore there may be a confusion why it is sigma r by a y. It's not actually, it must be 2 times of sigma r by a times of y, right? This part is clear, no doubts are there. Yes. That's it, gentlemen.